Okay, good. So everybody now is an expert in basic concepts in rigidity theory. So it's my pleasure to take you to the next step into a topic that has preoccupied me in the last about 6 or so years. So I am Iliana Străinu, and it is also a great pleasure to speak here. I am a Rutgers alum, and I spent here 5 wonderful years at the time when Dimex just started. And so it's great to be back after 22 years. I mean, I've been here once in a while, of course. So a little bit about my affiliation. I'm affiliated with a lovely Smith College in Massachusetts, and I'm also affiliated as an adjunct at UMass Amherst, where I recruit graduate students. So my graduate students are there, so I just wanted to make sure that their affiliation is also mentioned. So the work that I'm going to present is primarily a survey of work done with Ciprian Borcea, which I just realized that something is missing. Okay. For some reason, things moved a little bit. So primarily a survey work done with Ciprian Borcea from Rider University. And let me start with the motivation. That's the problems that underlie the topics that I will be talking about come from various challenges in crystallography and material science. And I'm mentioning the first 2 of them in the beginning as motivation, and I'll get back to them and to the other 2 towards the end of my talk. So displacive phase transitions in crystalline matter. So here,
do you want
no, I don't want,
you don't.
because I need to control certain things on my computer. So here are 2, it's basically one crystal called cristobalite. And the images are taken from Wikipedia, but the structures actually can be found in the crystallography open database. So they are real structures solved with X-ray crystallography, some of the oldest that have been solved. And you find that usually how these things are presented, of course, they are presented in a file with all the coordinates and connectivity information. But what you get is the information in a unit cell and then images of slightly larger crystals. And alpha cristobalite comes up in 2 states, the so-called alpha cristobalite and the beta cristobalite, and they have the same bond structure, so atoms connected by bond, and this forms a framework in the sense of frameworks that we have seen before, but there are different positions of the atoms, so this is a displacement. And physicists, chemists, material scientists call this displacive phase transitions. So of course the displacive phase transitions usually happen under the influence of external factors like temperature, pressure, and so on. So the earliest reference we could find about displacive, about the fact that crystals can have this kind of displacements is in a paper of Linus Pauling on collapsing the sodalite framework from 1930. And I'm pointing out to a few ideas here. So he refers to the framework of the cristobalite, so which I'm showing here in a skeleton, so it's hard to display 3D structures. The framework, while strong, is not rigid, and there are no strong forces tending to hold it totally expanded. In sodalite, the framework collapses. That's the terminology, and that's what the crystallography literature has adopted ever since. They talk about collapsing of structures. And he describes how the tetrahedra rotating about the 2-fold axis and so on. So now the X is actually, the tetrahedra represent positions of the oxygen atoms, and here we have another atom, usually in the beginning, aluminum or silica or whatever. So this partial collapse of the framework reduces the age of the unit cell. So he also talks about a change in the unit cell of the crystal that was observed with that kind of collapse. So here's how you find this tilt. They refer to it the classical tilt for sodalite frameworks. That's how it is usually depicted in the crystallography books. So this is an illustration from from a mineralogy magazine, and it's the view from the top, and you can see that it tilts. Yeah, so there is a motion there, and this is viewed in a 2D projection. Okay, so that's the first motivation. So now let me tell you about the second motivation. So this is a concept that we came across when working on these things, and here's what it is. It's very intuitive. It can be described intuitively. The material science literature defines it in terms of elasticity theory, in terms of negative Poisson's ratio, and usually this is something, a property of a material, and it's usually measured. So you infer it by measuring and deciding whether the material has auxetic behavior or not. So the intuitive definition is that if you have two orthogonal directions, right? So the natural material, I mean the more natural behavior, you expect that if you pull, the material will get thinner. So it'll be something like this. Oops. Okay, so you pull it and it becomes thinner. Okay, so that's what you expect. So now in an auxetic material, it's the opposite. So notice, you pay attention to what happens here. It's not that this is going to expand enormously, but it's not getting thinner, it just grows a little bit more, yeah? So this is the behavior of an auxetic material. So you pull, and it gets, in this case, a little thicker, okay? So now, these two videos come from the website of a group in the UK that has been studying these properties for years. I'll give the references a little later. But they also have a model, an explanation, and also the intention of building synthetic such things. And here's the model. So let me continue with this one. So the model is it's a crystalline structure. It's a periodic structure. You see here just a little piece of it. And you see this framework, when you pull it in one direction, it becomes thinner in the other direction. Okay, well, the other one. Hold on. Okay, should be looking here, actually. And the other one is, so this is the model. So it's the same network, but in a slightly different placement, in a slightly different realization. It's a periodic structure where each piece is hexagonal. This is called the hexagonal honeycomb, and this one is called in the literature the reentrant honeycomb. Okay? Good, so this being said, these materials were known for over 100 years. The first reported synthetic material appeared in Science in 1987. They are reported to have enhanced mechanical properties, which leads to many applications, biomedical applications, sensor actuators, filter, shoelaces that won't untie, and many other exciting things. And here's the reference for this, where I took these videos. So this is the so-called reentrant honeycomb. And this is another very well-studied model, so the rotating squares, it's called. But the punchline is that, so this is, once again, I'm repeating here the informal description of auxetic. A stretch in one direction leads to a widening in a second direction, usually orthogonal. And what I will do in this survey talk, I will present a theory of periodic rigidity of frameworks, rigidity and flexibility of frameworks, which helps analyze mathematically idealized frameworks of concrete crystal structures. And what I mean by that is no reference to chemical or other material properties, so that we can decide rigidity and flexibility properties that are purely depending on the geometric constraints. And this, in particular, this will yield an infinite supply of auxetic designs, which basically what I have shown you before are the two best known, but it's only a handful of such designs that were known in the literature. Okay, so let me start. So I'm going to talk about periodic frameworks. I'll start with examples, then I'll go into definitions. And I know this is the most painful thing in rigidity theory because it's a lot. So fortunately, Bill has done the preliminaries, and so we'll just have to extend some of those definitions to the periodic setting. And I'll tell you what the subtleties are rather than going into formulations and equations and matrices and so on. And the theory is only as good as the implications it has. So I will tell you about the theorems that follow from the setting that we have developed, and I'll get back to some of the definitions of the applications. So as I said in the beginning with these two examples, with the alpha and beta cristobalite, these are two different conformations of the same framework. So one interesting question to ask is it possible to continuously deform from one to another? That's one question. So here's, again, from the same site. So here's, this time it's again, it's a simulation of a possible, oops. Okay. Okay, it's a simulation of a possible collapse of the cristobalite. Of course, it doesn't happen as dramatically, but in simulations, you can do everything you want. Okay, so periodic frameworks. When we define a periodic framework, we are talking about an underlying graph, and the model can be bar-and-joint, as Bill has presented earlier, or we could have a model called body and bar, and several others. So basically, it's a mechanical model where the objects have some rigid, some fixed pieces. The pieces can be distances between certain nodes, certain joints, or can be entirely rigid bodies connected by bars that preserve the distances. So the framework, besides the graph, the framework is placed in a dimension. So this is in an ambient space, and this is in dimension 3. I'm illustrating here with a very famous class of examples, the zeolites. They are represented usually as vertex-kissing tetrahedra. So you can view these edges of the tetrahedron as bars, and the joints, which are oxygen atoms that allow rotations, are where the tetrahedra kiss. This is another crystal, the so-called Persian blue, which has this structure that naturally leads to this model of body and bar. So the crystals can also be 2D, like the famous graphene, and well studied nowadays. So we also have periodic frameworks in 2D, and they can be bar and joint, body and bar, and so on. So given such a periodic framework, first of all, I want to emphasize a periodic framework means an infinite framework. So think about it as extending to infinity. The first question you may want to ask, is this actually rigid? Does it flex? Okay, so let's try. So this one actually has a flex. And okay, it's flexible. Next, you want to know, well, how many degrees of freedom? I mean, how many ways can I tilt it? So for instance, is Pauling's tilt the only possibility? Is the simulation that we have seen of sodalite the only one in which the sodalite can collapse? Is the reentrant honeycomb auxetic in just one single way? So we want to understand this theory. And not only that, but during the motion, I want you to pay attention a little bit to it. So certain pieces, certain parts of it, like these parts here, oops, again, these parts here stay rigid. These are two triangles in 2D are rigid. So they move like rigid components. So I'd like to understand what are the rigid components if the whole thing is flexible. Good, so now let's do the definitions. I'm going to focus primarily on bar and joint. And I'm going to try a little bit of little comparison with the challenges in going from the finite case to the periodic case, because it took a while before the theory settled down and before the definitions that I'm going to present here proved their effectiveness. Meanwhile, people tried various things. So here are the basic concepts. We have a graph, vertices and edges. We have a framework, meaning a placement of those points in the plane with the maintenance of the edge lengths. all throughout. And this framework may have a deformation. So this is a continuous deformation. So it's sometimes called flex, continuous deformation, whatever. And there is a concept of infinitesimal deformation. And from here on, you need to talk about what is the set of all the possible placements, the so-called realization space. And the realization space always contains rigid transformations of the object, so we factor that out, and we call that the configuration space. And the configuration space can have different connected components, and we call deformation space the connected component to which our framework belongs. And these concepts, the basic concepts here, graph and others that appear along the way for genetic structures, they are coming from graph theory, combinatorics, matroid theory. Concepts such as realization space, configuration, deformation, and so on, tangent space, smooth points, singularities, and so on, they are on the realm of real algebraic geometry, and sometimes in order to be able to say something meaningful, you have to switch to complex algebraic geometry. So it's not that the real world is real, but we have to go to formulations that make the discovery of properties and the proof of the theorems feasible. And then, in this context, we define what it means for a framework to be rigid, what it means for it to be generic, in particular, not a singular point on the algebraic variety, what it means to be flexible. So it belongs to a one-dimensional curve in the deformation space, what it means to be stressed or over-constrained, and so all these are concepts from real algebraic geometry. And then, as usually, these things are difficult to handle. So solving systems, large systems of algebraic equations, especially over the reals, it's a very challenging problem. So we are in the realm of Gröbner basis and algorithms. They're algorithmic solutions, but they would work only for very small structures. So as usual, in order to derive something interesting, you linearize. So you take the tangent space at your particular configuration, conformation, and we get into things like the Jacobian, which is an incarnation of the rigidity matrix that you have seen earlier in the morning in the talk of Bill. And we talk about infinitesimal motion, so just the tendency of the points to move in a coordinated fashion. And also we talk about infinitesimal dependency, which is the stress that also appeared in the morning. And now these spaces are algebraic objects, and they have a dimension. So the whole theory has to be set on a proper footing so that we can properly define what it means that this is the dimension. And the dimension gives us the dimension of the configuration space or of the deformation space, gives us the degrees of freedom of the object. So, or the degrees of dependency. And along the way, we also have a concept of duality that belongs to linear programming, linear optimization, and this is very useful for proving things, for connecting the primal formulation in terms of infinitesimal motions to the dual formulation in terms of stress and deriving very interesting properties that I will talk about towards the end. And finally, there are more advanced topics that will come up in my talk towards the end that I will need concepts from semi-positive definite theory, group theory, matching, then flow algorithms, SDP, and you name it.
I'm sorry, what is semi-positive definite?
Semi-positive definite. So it's positive.
It's positive semi-definite.
Positive semi-definite.
Is it?
Yes.
Oh, okay. Okay.
Okay. Isn't it? Don't you call it SDP?
SDP, but this would be SPD.
Anyway, I'm not good at these three-letter words, as Bob pointed out yesterday. I'm always, anyway. So I just didn't have time to write all that down. Yes, thank you for noticing. So let me go back to the very basics. And believe it or not, this is what took the longest. So the idea is to give a proper definition of what is a periodic framework and what is the deformation of the periodic framework, so that the rest of the theory can follow naturally, can follow along the lines that have been followed in the finite case. So let's see what are the difficulties. So I want to start by defining a periodic graph and then a periodic framework. Okay, so first of all, remind you, a periodic framework is an infinite graph. So you'll see something like this. So you look at it and you notice that certain things are repeating. So that is usually the maximal periodicity is usually what catches your attention, but that's not the only one that you can take into account. So a periodic graph, in other words, is a simple graph, infinite, so vertices and edges, infinite sets. It's locally finite. We have to restrict it to something. I mean, as a computer scientist, I want things to be finite. I'm not saying that you cannot study it in other settings, but let's restrict ourselves to something that we can do algorithmically eventually. So it means bounded degree. And on the infinite graph, there is a group that acts. The group is free, abelian, has a rank D. Yes, it's you choose it. There may be several groups acting, you choose it. And it acts without fixed points. And with the action of that group, there is a finite number of vertex and hence edge orbits. So these are the basic conditions that we enforce on the graph. So for instance, in this case, every vertex has degree less than 6, it's finite. The group that acts here has rank 2, and I depicted here in the same color the vertices that belong to the same orbit. So you see we have 3 colors. Red, blue, and green, so these are the 3 vertex orbits, and those are the generators of the group. And there are 6 edge orbits, also depicted with similar colors. Okay, so that's the graph. So here's probably the simplest one that you can imagine, right? So this is the square lattice. So finite degree 4, rank 2, 1 vertex orbit, 2 edge orbits. And what I have chosen here is what is called the maximal periodicity. So that's the largest group that acts on it. But nobody prevents you from choosing other groups acting on the same infinite graph. So I want to emphasize from the very beginning that specifying the periodicity group is important. So the theory of periodic frameworks that we'll be developing depends on the choice of the periodicity. So for instance, for this structure, this is the maximal periodicity with 3 vertex orbits and 6 edge orbits. And I can, for instance, relax the lattice. You don't need to do it in the same way. It's just the index of the lattice that matters. And you could have, then you have a subgroup of periodicity, and this one has 6 vertex orbits and 12 edge orbits, and so on. So each one of them is, according to this definition, a different periodic graph. So graph is infinite graph together with a group acting on it.
Another question. So here what we're seeing is a geometric group because the graph has been shown in the plane.
Yes.
But I suppose that you could define the same thing without the framework itself and just the graph?
That's it. It's ignore. I mean, I have to draw it. You know, graphs have to be drawn. And it was easier to draw them with straight lines, and it was easier to draw them exactly in the way that they will be realized. But that's exactly what I emphasize. It's a graph without reference to the placement. So now let's place it.
What if, sorry, simple question. I don't understand what the group action is.
So,
what do you mean by the group?
Okay, so the group is what says that this vertex, so let's take the generators of the group. In this case, we have 2 generators, and say this vertex is obtained by applying the group element 1 to this, and this is what the red points are, all of them, right? So the group action in this case is given geometrically, but you can give it abstractly by saying these vertices are related to each other by this generator. These vertices are related to each other by this generator. This one is a sum of them, so that's where the group property comes in. So you are able to add and subtract the elements of the group, and they give you all these points, and all of them are obtained from just one, which is a representative. You can choose anyone as a representative in this infinite graph, and the group action tells you which ones are equivalent, are in the same, you can obtain by applying a combination of the generators. Okay? So it's just terminology from group theory. So here, the generator is not putting this and this in the same class. It's putting with a hop of 2. So it's a different group, that these two generators are different. So this and this are not in the same orbit because the generator takes it one hop further.
So, for example, one way that I could describe this group abstractly would be to label the vertices
Yes.
In a smart way, so that I would follow, for example, some integer 1, 2, 3, 4 for reds, for blues, and then I would have like a simple action on there.
I'm going to do that later, but I just wanted to point out that in the beginning, you are just given an infinite graph, yes? So let me go back to this one, right? So that's what you are given. It's your graphene, right? So, well, you have to you see the periodicity. How do you, okay, are these two the same orbit? Is this a periodicity that happens here? It's unclear, right? So you have to define what is the repeating unit. So crystallographers are very familiar with this, so they define a unit cell and so on, yeah? So now, abstractly speaking, in the language of group theory, we just have a group, but it's important to retain the group. And let me tell you why, because, again, for the motivation, I want you to, oops. I'm sorry, I don't know what direction I'm going. I wanted to, anyway, I wanted to go back to the cristobalite. So, because there, the phase transition, so the structure is the same, and there is a deformation, is the same abstract group that acts on the structure, but the size of the unit cell, the geometric realization of that group has changed. And that is a very critical aspect. Okay? So these are the subtleties in grasping this concept. But let me emphasize again, the periodic graph and the group are given. They capture the combinatorics, very much like in the finite case. The combinatorics was captured by that finite graph of the framework. So here we not only have the graph, we also have the graph together with the group action on it. Okay, so now with this, now we go to the framework. So now here it is geometrically realized. So again, we have the infinite graph with the periodicity group, but we have to place the vertices in the plane, and we have to define a geometric object corresponding to the action of the abstract group, and that is a lattice of translations. And so this time, this is really geometric, right? So this is a translation in this direction, a translation in this direction. That's the sum of these two translations and so on. And of course, it has to be a usual compatibility between these objects, yeah? So in other words, a periodic bar and joint framework is given by the infinite graph. So far, we don't like it as computer scientists. We cannot put infinite graphs in the computer. We'll talk about this in a minute. A group, abstract group, and that has to be well entrenched because the group will, and the graph will never change. We don't break bonds, they stay where they are. We don't change the action of the group. We want things to stay similarly to retain the periodicity. However, the placement may change by maintaining the length of the bars, and the periodicity can also change. And sometimes may even break. Okay, so let's see what we actually mean. Right, so this is the framework. Okay, good. So now let's become computer scientists again and talk about finite presentation of the infinite periodic graph, and I'm going to talk about the quotient graph and the marked quotient graph. So once again, I said, so now this is abstract. I depict it geometrically so that you see, but it's an infinite graph, and the group acting on it. So let me choose a group, gamma 1, and the group gamma 1 makes all these points equivalent. So they are in the same orbit. In the same equivalence class, you can get from one to another by the action of the group gamma 1. Okay? So I can choose another group, gamma 2. It's a subgroup of the first one, where only these vertices are obtained, are in the same orbit. Yeah, so as I said, we can choose different groups. And here's what we can do. We associate a finite quotient graph. So all the vertices that are in the same orbit, we choose a representative and put them in one big blob over here. And also the edges, representatives of the edges will have a representative here. So let's look a little bit at this picture. So under the action of the first group, all the blue vertices have one vertex in the quotient graph. All the red vertices have one vertex in the quotient graph. And if you pay attention, you see that sometimes we may have multiple edges. In fact, sometimes we may have loops in the quotient graph. So the quotient graph is a finite graph. That was our assumption. We have a finite set of orbits and vertex and edge orbits. And it's simple, but the multi-graph the quotient graph can be not simple graph. And here's, for instance, the orbit of this edge, and this is the representative of this edge. Okay, so it's clear? That's the quotient graph. So this allows for a representation of some information in the infinite periodic graph. Not all of it. Here's why. Because, so in the finite quotient graph, there is less information than in the periodic graph for the following reason. So watch this example. So this is a graph, and this orbit of this edge corresponds to this edge in the quotient. But if instead of this edge, I have this edge, it's still between a representative of the red and the blue. The other one disappeared. And this information can be not retrieved from this graph. So distinct periodic graphs may have the same quotient graph. So there is less information in the quotient than in the infinite periodic graph.
Why wouldn't this, if you had both edges, you meant?
No, this is one graph. This is one. This is another one. They have the same quotient graph, yes? Okay. If they had both, then it would have been a double, yeah? Okay, good. So now that's a concept, and it's critical in what I will be talking about. So now, if we put some marks, some information on the quotient graph, actually we can have the whole information in the periodic graph captured in one finite object. And that one is not a canonical one. You have to choose a certain labeling, just as you said before. And here's what I have chosen it, right? So these are, if you think about one orbit, we choose an arbitrary vertex to be labeled, in this case is the rank 2, so there are translations. I'm going to label the vertices with elements from Z2. So this is sort of the origin, and I will be choosing it as my representative. And then if I go 1 or 2 in this direction, so I'm applying the first generator, I'm applying the second generator, and here are summations of the generator. So I'm just representing them with integers, positive or negative integers. Okay, so now with this labeling, which I can choose independently for all the vertices, nobody prevents me. There is no standard way of doing it. So for instance, here I have chosen as the 0, 0, the representative for my orbit to be this vertex. So I have a labeling. So based on that labeling now, you can look at an edge, orient it somehow, and if it goes from 0, 0 to something else, use that label on that oriented edge. And again, this is not a canonical way. There are many ways of doing this. But it's a finite presentation. Yeah, there are many finite presentations of this. Okay, so for instance, now we can distinguish between those previous graphs. So this one has a different label than the other one. Yeah. So so we summarize this that we can have these two presentations of the periodic graph. We can give you the quotient graph and we can give you the Mark quotient graph, and both are finite graphs. And this one contains the same information as in the periodic graph, right? So now I'll have to talk about the placement of the representatives and the choice for the translation. Okay, so again, a piece of terminology. We use this terminology that later on will be used for another concept, and I'm emphasizing so that you are not confused. So when I place marks on my quotient graph, I'm saying that I'm lifting the quotient graph. Yes, it's lifting from a finite case to a periodic case. So it's just a piece of terminology that you'll find it in our papers. Okay, so with this, I also want to make a little bit of comments, historical comments. So the concept of a periodic graph, quotient graph, periodic placement and so on has been heavily studied in the crystallographic literature. So there are people who studied ways of representing, of placing abstract graphs with TAT-like embeddings, Cotani and Sunada, Delgado Friedrichs, and so on, many people. There is software that does some of these calculations. The marked quotient graphs have appeared in the literature. To the best of my knowledge, Zaslavsky used this as gain graphs. There is in the sphere packing literature, these are special cases of these things studied there. Also, in some of these literatures, periodic graphs are viewed as graphs on the torus. And I'm emphasizing is the graph that you think about realizing it somehow. Usually it's a graph on the flat torus, flat. If you think about realizing it, but nobody prevents you from realizing it on a donut or whatever. And also periodic frameworks viewed as frameworks that are on the torus, and by this I mean a given torus, flat torus, because they use a metric, and in dimension 2 have been used in the circle of Walter Wiley, in particular in the thesis of Elisa Ross and other people who are here. Yeah? Okay, so let me now move to the next level. So the next level is what are the deformations of periodic framework, and that's where the whole subtlety comes in. So here's an attempt number 1. Okay, so here's the most basic periodic framework, and you can deform it this way, or that way, or that way, or that way, or that way, in many ways, and think about this infinite thing. And in fact, you realize very soon that this framework has an infinite, in fact, a countable dimension of the deformation space. Each one of these deformations, it's independent and generates a very large space of deformations of countable dimension.
Wait, what is the dimension of the deformation space?
Independent, okay. Algebraically, you have to think about behind this are equations that set up the lengths of all of these, and they're looking at the space. Now you will have an infinite set of equations that tell you that each of these bars have to maintain its length. Yes? So this infinite set of solutions allows a basis. We are not quite used in computer science to think about dealing with infinite things, but yeah, for mathematicians is the piece of cake. So that's a concrete, well-formalized concept that I will not go into it because I'm going to avoid doing it.
Why infinite?
Because each one of them can be, think about this. This is a 4-bar mechanism. It has a flex. Next one has one. Next one has one. So in fact, the whole row independently, it's an infinite number of squares. Each one can be deformed independently. And also a column can be independently. It's a countable set. It's a countable set. Okay? So quite a lot. Too much for us. Okay, so we want something finite. So that's the first attempt. So of course we could study that. Nobody prevents us. But as computer scientists and as people who want to do things on the computer, we want something finite. Yeah, that's the object that we are after. Okay, so this I'm saying that is not a good theory from our point of view as computer scientists. I'm not saying mathematically it's a good theory, and it can be definitely studied. To the best of my knowledge, the first paper on infinite frameworks was by Owen and Powers, and they studied frameworks that are even crazier than this one. So they were not even periodic, they were infinite, but the placement had accumulation points, all sorts of crazy things, yeah? So you can use heavy mathematics to study those objects. Not me, I'm a computer scientist, I want finite things. Okay, so that's the goal. Good, so now let's look at a bad property, something that we don't like about this, is that these deformations don't preserve periodicity. Yes, they flex, but we've seen in cristobalite that nature actually flexed that somehow, that crystal, and it was periodic here, and the other conformation is still periodic and seems to preserve some periodicity, so why not study only those that preserve periodicity? So that's what we like to do, okay? So here's a summary of the basic concepts. In the finite case and in the infinite case, everything goes according to a recipe. You define the graph, you define the framework by a placement, you define the realization space in the finite case. Well, in the infinite case, the realization space has to be defined with a much heavier mathematical machinery. It's an inverse limit of taking the restrictions on finite subgraphs, and it's a complex mathematical object. Why do it? We are computer scientists, we want things that are finite. Okay, and the rest is like a recipe. You define the, based on the realization, define the configuration space by factoring out the trivial rigid motions, and the same with the deformation space.
What is E of D?
Their edges. Oh, E of D, sorry. So I'm using the Euclidean space in dimension. It's the group of Euclidean motions. Yeah, sorry. Okay. So I'm going quickly over this because I'm not going to go into heavy details. This is the kind of thing that you have to go and read details of the paper. And also, by the way, it also helps that when embarking on this work, my co-author is an algebraic geometer. So I wouldn't dare to utter certain sentences without the backup of somebody who really understands all the implications of the statements and the theorems. So there are very subtle things behind the scenes just to set up the definition. Okay, so in this case, in the infinite case, as I have intuitively shown you, the dimension which corresponds to what we call degrees of freedom may be infinite. So here's the second attempt at getting something finite. So we can view the periodic frameworks on the torus. Yes, so it's, why think about the whole thing? Let's just restrict, choose a representative, choose a unit cell, and that's the torus by identification of opposite sides. And this is what was, to the best of my knowledge, started in Whiteley's circle, and that's what Elisa Ross's thesis was about. To the best of my knowledge, and Bob can contradict me, the circle packing community also works in this setting, and so on. So in this setting, the periodicity lattice is fixed, geometrically speaking. Yes, the flat torus is, you choose the unit and you don't change it. So changing it, so people started calling what we are doing now the flexible torus. I'm not sure that's the right terminology because the metric of the torus changes, so you have to be careful. So I prefer you to think that thinking on the torus is given. Yeah, so the metric of the torus is fixed and so on. So you need that in the sphere packing in certain communities. There are also, in developing a coherent deformation theory in this setting, you get to various paradoxes and so on. So let me not get into this, because let me tell you what our definition was. Okay? So this is a definition that appeared in 2010, and we have worked with it ever since. So I think that the definition proved its value by the theory and the consequences that it entailed. So the definition is not about the framework per se. It's also about the deformations of the structure that you are looking at. So what we call the deformation theory of periodic frameworks. So the definition is the following. We have a periodic structure of rigid bars connected by joints. Yes, periodic according to the previous definition, but it is constrained to move in such a way that it preserves the periodicity group, gamma. So the abstract group. So here's what you should retain from this. Yeah, so if I give you this, I have not given you all the information. I have given you a graph with a placement. I have to give you the periodicity. And in the previous animation that I have shown you, I have not shown, you have not seen that the lattice actually is also the representatives of the generators of the lattice are also deforming. Yeah, so this is flexible indeed, and during the flex, the periods also change. They can change the angle between them, they can get longer or larger, so the unit cell changes. So that's why people probably call this the flexible torus. It's basically the torus is somehow stretching, contracting. I don't like it. So we work in the infinite in the periodic setting, and everything is more clear. Good, so in short, here's a summary. We have the graph, the group, the placement of these two things, and we allow only deformations that preserve the periodicity, and the lattice of the transformations can deform. And under these conditions, the configuration space is the set of all placement up to trivial motions, and it can be formulated as a finite set of algebraic equations. We got to the finite setting. It can be formulated actually semi-algebraically. The deformation space is the connected component, and we say that a framework is rigid in the sense of periodicity if the deformation space is an isolated point, otherwise it's flexible. And the space of infinitesimal motion is the tangent space to this algebraic object, and the stress space would be the space of the duals. And I'm going to get later to some of these concepts with a more intuitive formulation, but I wanted just you to see that it is basically a methodology for defining the useful concepts, and they translate from the finite to the infinite and to the periodic case. So once again, I'm emphasizing specifying the periodicity group is important. It's not important if you don't care about the deformation of the structures, but as we will see later, different periodicity may give you different rigidity properties. So that's why it is important. Yeah. So if you choose deformation that preserve a certain periodicity, they may be different from when you restrict to a sublattice. So here's a very simple example, just to get an intuition. Maximal periodicity means when all these vertices are in the same orbit. Yeah, so this is a very simple graph to one orbit and two orbits of edges, and there is only one. There is this deformation, yes, that if you preserve, okay, yes. So because the periodicity is their edges corresponding, they are also periods, the length of the unit cell does not change. So it's only the angle that changes. So basically this has only one deformation, 1 degree of freedom, periodic deformation with this periodicity. Whereas if I relax the lattice, so I'm relaxing now to a 3 by 3. Yeah. So in this setting, view that this vertex and this vertex are equivalent, but now these are not. This and this are equivalent. So the periodicity now is this. These are the two generators. So now in between you can flex. And you can count, it's a finite structure. It has 5 degrees of freedom. So overall, we'll have the same infinite graph, deform under this periodicity will have different flexibility properties. Okay, good, so that's a summary. Periodicity is part of the definition, allow only deformations that preserve the abstract group, and the lattice, the representation of the lattice of the periodicity, the lattice itself may also deform, not just the positions of the vertices. Okay, so the rest of the talk, I want to demonstrate to you why this is a good theory of periodic deformation. And it's a good theory because, number one, allows for a finite treatment. It allows theorem characterization of Maxwell-Laman type, very much like Bill introduced them in the morning. So we have generic structures that can be combinatorially characterized. And they can be characterized in terms of the quotient graph. And I will not have time to go into the details, but there is a very subtle connection between rigidity of finite structures and rigidity of periodic structure, and there are some implications there. Anyway, this theory has a dual theory, a stress theory. So everything that you heard before about stresses can be also computed here. And this theory leads to generalization from the finite case to the periodic case of a famous theorem of Maxwell from the 19th century, the so-called Maxwell polyhedral lifting theorem, and leads to a theory of expansive motions. And these have implications in the design of auxetic materials. And I'm going to get that towards the end of my talk. This theory also extends to periodic body bar frameworks. So not just bar and joint, and this has implications in our analysis of flexibility and rigidity of periodic structures, of molecular structures, because most of them can be modeled correctly in this fashion, and leads to new concepts, auxeticity and ultra-rigidity, that I will define later. Also, they lead to Gould algorithms. We have having a Maxwell-Laman type of characterization in the sense of the counts. So Bill presented in the morning Laman's characterization, and maybe you didn't get into details of the algorithms, but although the characterization seems to be exponential, actually they are very good, efficient algorithms based on variations of matching algorithms, network flow, and so on. There is the famous or infamous Pebble game algorithm that can be adapted, and so on. And also, it leads to good algorithms for testing infinitesimal auxeticity, and that will be towards the very end of my talk, where I will be using semi-positive definite on a finite dimension situation. And applications of the theory is that they model phenomena that have been observed in the crystallography and the material science literature, displacive phase transitions, auxetic behavior, and also kinematic parameters of crystal structures without direct reference to chemical and physical properties. So we are just using the geometric constraints. And in particular, in the end, I'll show you that we can design an infinite supply of materials, new materials with non-standard properties, like those shoes that don't unlace, whatever, the auxetic materials. And all this work is based on papers that we have published in the last 6 years. So let me get quickly to this property. So let me first set up the correct background by stating that the realization space of a weighted d-periodic graph, so I have the graph, the group, and I make the length. I fix the length this time. Yeah, so they can come from a placement, and I start with the placement, but I fix the length. And the realization space can be identified with the solutions in, so this is the general linear group in dimension d. This is r to the power d, and n is the number of vertices in my quotient graph. And these are my variables. And this is the action of the periodicity. That's the generator of the translation lattice. And basically, this encodes the fact that a certain edge length specified by this specified marks on the mark quotient graph, it specified that this has fixed edge length. But the quotient graph has finitely many, so we have finitely many such equations. It has finitely many vertices, so we have finitely many unknowns. And we have, if the graph has n vertices and we are in dimension d, then we have dn unknowns for the positions of the vertices, and we have whatever number of variables we need to specify the general linear group, the translations. So these are for specifying the generators of the lattice. So that's the formulation. So we reduce it to a finite case. So as I said, it's good because, not because it's ours. Of course it's good, we love it, but it allows for a finite treatment of rigidity.
May I ask you just notation-wise, why do you use the angular brackets?
It's dot product. So length, dot product, two vectors, yeah? Okay, it's just, we happen to I picked this up from the paper, and there's the notation we use there, yeah? It's harder to type in PowerPoint. Okay, so a corollary, and again, do not get intimidated by this terminology. I had hours-long discussions with Cyprian, making sure that I understand what they are, but I won't be able to explain them to you in a fraction of a second during this tutorial. You have to sit down and grasp the real algebraic geometry literature to understand why this has to be complex so that we can count that correctly define the dimension. But real is embedded in the convex. The realization space, we view it that way. And it's a quasi-projective. And again, it's fine, it's correct. But the punchline is that it allows you to say that all of its irreducible components have complex dimension at least that much. Yes, so we can count, we can use results from algebraic geometry to say what are the dimensions of the complex components of that space. So where n is the number of equivalence classes of vertices, m is the number of equivalence classes of edges, and so this is the first instance of a Maxwell count type of thing that we see here. Yeah, so in dimension 2, this would be 2n plus plus 4 minus the number of edges. So that would give you the dimension of the configuration space, of the realization space. Okay, so in this case, for instance, dimension is 2, 5 vertices, m edges in the quotient graph. So we know that its dimension of the realization is at least 4, but the trivial motions in space in the plane are of dimension 3, so 4 minus 3 is 1, so we anticipate that this may have a motion. Now, in a particular realization, whether that actually exists or not, it depends on the realization. But in other words, we expect flexibility. So if you look at this graph, so we calculated, computing the degrees of freedom generically, yes, we expect at least 1, and indeed, this is it. And in fact, this is it. Okay, good, so now here's a summary. Finite case, infinite case, projective case. It's just for you to take home, but the idea is once we have the good definition, the rest follows from this recipe of defining a rigidity theory. So, and the punchline is that in this case, we got to something where we can talk about finite dimension, finite degrees of freedom. Good, so let's move on. So let me see how much time I have.
Around about 20 minutes.
Wonderful. So the next thing that I want to tell you is a combinatorial Maxwell-Laman-like characterization. So we have seen earlier in the morning that for finite graphs in dimension 2, there is this famous theorem of Laman, obtained about 100 years after Maxwell gave his counts, and characterizes the graphs that are minimally rigid in dimension 2 as that hereditary property with the counts. And here's the counterpart, so we call it a Maxwell-Laman type of characterization of periodic, minimally rigid, Barenjoin graphs, and here it is, hold your breath. It's arbitrary dimension D. Okay, so hold your breath because there are subtleties hidden behind it. We know from Bill's talk that in dimension 2 we have a Maxwell-Amann theorem, but dimension 3 and higher, in the finite case, nobody has a good characterization. I'm giving you here a generic characterization for arbitrary dimension, but of course there is something hidden under the rug, so I'll tell you in a moment what it is, but let's read it. So you give me a multigraph, can have double edges, can have loops, and vertices, and exactly, so we are talking about those that satisfy with equality. Dn plus d choose two edges. And this multigraph is the quotient graph of some infinitesimally minimally rigid periodic Barenjoin framework in dimension D, and this is for arbitrary dimension D, if and only if it contains a subgraph with, when I say Dn minus d edges and sparsity type, I mean exactly the condition that was phrased in the morning, in the sense that it has exactly, the subgraph has Dn minus d edges, and hereditarily on subgraphs, any subgraph of n prime vertices has no more than Dn prime minus d edges. So that's a hereditary Laman type of property. Okay? So this is the thing that made us confident that this theory can lead somewhere. We got a good characterization. So now let me be a little bit more specific so that you understand. I remind you that the quotient graph may correspond to many periodic graphs. Yes? So I'm not talking about an infinite periodic graph. I'm saying the following. If the quotient graph has these properties, then there will exist some periodic graph. For instance, it might be this, where I placed an edge here between these representatives, or maybe this one, where I placed an edge here, or some other one. But definitely we guarantee that most of them will be generically, periodically rigid, minimally rigid, if the conditions of our theorem hold. The key there is the genericity. Okay, so now, this is a very thorny issue. So whenever we get to discuss genericity, oh my God, we are not getting into fights. It's just that every problem is, its generic is whatever makes your setup work. So I discussed this at length with Ciprian. As an algebraic geometer, he says, well, in algebraic geometry, that's what it is. It is the Zariski framework. So you take the complement of the zeros of some polynomials, for instance. Yeah? And that set of polynomials can be a finite set, an infinite set. In the very strong Lovász-like genericity that the people in global rigidity use, they take all the possible algebraic equations. But we don't need them here. We are working with a finite set, and the conditions that we have to throw out are finite. So that's the reason that we can do things on the computer very happily. Yeah? So the genericity is handled in the same way, at least for finite cases. Now, here, here comes something that's a little weird, because, so let's read, this is a reformulation of the previous theorem. So if you have a graph and the Gaussian graph contains a subgraph, blah, 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 a generic lifting, so meaning that you may lift your edge to be between this representative and that this representative end. You may lift it to any of the other representatives in the same orbit. But generically, except for a measure zero situation, all of them will be will have the properties that I'm saying. They will be generically, they will be a smooth point on your variety. Yes.
I'm confused. Isn't the lifting a discrete object?
No. So
Isn't it which one I connect to?
it is, but I can connect it. So the space of all the possibilities is infinite.
Right, but there's only a finite set of vertices that I can attach myself to.
No. Yes, a countable one. Yes, exactly. It's a countable one. Yes.
So, I'm still confused then.
Yes, so I was prepared for this kind of questions because it's been a source of confusion ever since we published this. And I think that the best way to address it is to sit down with a piece of paper and discuss it. Okay?
So in other words, you're not prepared to answer.
No, I am prepared, but then I will not get to the interesting part that I want to show you. Okay? If you give me time and we have another setup just for this, I could do it.
Another word.
Yes. So I have a limited time and I want to tell you about more exciting developments. So this is just the basic thing. So for the moment, take it on faith because we have published it in a serious mathematical journal and I have grilled Ciprian all the way to make sure that the definition is correct. It was for me, myself in the beginning. So he has the mind setting of an algebraic geometer, which I have to confess, I don't. I think combinatorial. So I was pushing for the combinatorial characterization. He was pushing for the theorems that would prove that. So together we managed to get it. So it is, you have to sit down and I hope that the slides together with the animations will tell you what exactly all those ugly notation in the paper means. And with that, I hope that you'll understand what this genericity means. Okay, but please allow me to tell you the implications because I think that they are very exciting. So, good. So, and that's I wanted to remind you. So that's where the lifting is this marked graph. So we have to choose coefficients, and those coefficients are chosen. They are variables in our setting. It's just that what confused the people is that these variables are over z, are integers. But who prevents you from taking them over the reals? And then just write the conditions, algebraic conditions in terms of those. And as in the usual sense, in the Zariski sense, you are in a complement of those inequality, of those conditions where the rank of your matrix drops. Yeah, so that's it. It's that simple as that. Okay, so with this framework, so you see I spend most of my time making sure that the foundations are correct. So now let me tell you the consequences. So this allows for a rigorous combinatorial treatment of rigidity analysis on generic periodic frameworks. Yeah, but in this setting. So now let's see. So what are the consequences? This theory has a dual, a stress theory, and also a periodic Maxwell lifting theorem. So let me tell you about this. So this is a beautiful theorem of Maxwell. So Bill referred in the morning with to his work on setting these conditions, but this is a different paper. So he has 2 or 3 geometric papers besides his work in physics that made him a famous physicist, but he had a very strong geometric intuition. So let me tell you what this theorem says. Instead of reading it here, here's what it can be explained. So this is Maxwell theorem is about finite frameworks. So here's a finite framework, and the colors refer to stress, to the sign of the stress, and the stress is an assignment of that appeared yesterday in Bob's talk, the stress. And in all this work on global rigidity and universal and so on. So I'm not working here with numbers. I'm just retaining for the moment the sign of the stress. It's an assignment of numbers. So this edge vectors scaled by those constants are in equilibrium. So if a framework in the plane has a stress, then Maxwell theorem says it's an if and only if the graph itself has a lifting in 3D, so that the faces, so this is about planar graphs, non-intersecting graphs. So the faces lift to planar faces of a polyhedral surface that projects to you a graph in such a way that the sign tells you whether this is a valley or a ridge edge of the lifting. So let me get to a 3D animation of that because it's easier to view here. So this is my graph, and this is the lifting, and that's the projection. Okay? So here's another one, and this one now has ridges, mountain-like, and valley-like, and they are differently colored. And the Maxwell theorem, actually, this extension with the signs, to the best of my knowledge, is due to Crapo and Whiteley 100 years later, as usual. This corresponds to the sign of the stress on the original graph. Okay? So this is the theorem that we want to extend to the periodic case. Okay? So this is the demo. And so here's our periodic version of Maxwell's theorem. Before stating the theorem, let me show it to you, okay, with the pictures. So this is a planar periodic graph. And I'm claiming that this graph has a periodic stress. We'll have to define it, but I'm claiming it has. Okay, we can compute it. It also has, according to a posteriori after our theorem, it has a periodic lifting. But in fact, you can see the lifting. Do you see I colored the faces in the same orbit with the same color, and I bet you can see the cubes jumping at you. Yes? So the correct picture would be this one. Yes, so this is the 2D version, and that is the lifting of that as a periodic surface. So let me, again, illustrate it in Mathematica. So this is an illustration of the periodic Maxwell. So I'm claiming that this periodic graph here in dimension 2 has a periodic stress, and I'll have to define that. And according to this periodic version of Maxwell theorem, this one has a periodic lifting. Now, the periodic lifting, you sort of see what it is that the heights at which the vertices in the same orbit are lifted are equal. Okay?
10 minutes.
Good. Okay. Okay, so let me show you another one. So this is the same graph, but in a different placement. And I colored it so that you can have a better view. And I bet that none of you sees a polyhedral surface here, because there is none. That graph doesn't have stress. And with a stretch of the imagination, you may view these faces, but not as flat faces. And your vision does not cheat you because it's a theorem. That one is not a lifting. So here's our periodic version of Maxwell's theorem. A periodic non-crossing framework supports a non-trivial periodic stress on its edges, if and only if it has a non-trivial periodic lifting to 3D as a polyhedral terrain. So what is a periodic stress? I'll have to define. And what is a periodic lifting? I think that this one is clear because it is basically all points in an orbit are lifted to the same height. So what should a periodic stress be? Yes?
Does the original theorem require, I missed something.
Yes.
Does it require non-crossing?
I originally formulated with non-crossing, and then there is another construction in another paper of Maxwell on what is called the Bow construction, where you actually generalize it for crossing. Yeah, but let me formulate it for non-crossing because it's easier to state things, okay? Good, so what should periodic stress should be? Definitely, so it's an assignment of weights, and the weights have to be periodic, yeah? And definitely should be an equilibrium stress. So whatever weight you are assigning to these weights with times this should make an equilibrium at every vertex. Definitely it has to be an equilibrium stress. Yeah? Okay, good. So far so good. But then we have a problem. So I can show you that this one has an equilibrium stress, but can anybody argue why this one doesn't have a lifting? It's an elementary argument, right? Because if you assume that one of these lifts, yes, which one should be? Maybe this one, and that one should be lifted at the same height. And then what about this? Has an edge here and there. So in the end, this one actually has only the trivial lifting. So we need something else. So the equilibrium stress is not enough. That's the punchline. And this one definitely cannot have a periodic lifting, but in fact, it has a lifting. We can give it, I mean, you can look in our paper, but there exist non-periodic liftings of periodic stress frameworks. So for instance, the Delaunay-Voronoi diagrams. So this one actually has a lifting on the paraboloid. It's a Voronoi diagram, actually. And it's dual, the Delaunay triangulation. Anyway, so the periodic stress should be more constrained the equilibrium stress, and how? And the answer is, and it's technical, and I'm not going to write formulas here, so the periodic stress is defined as the dual of periodic infinitesimal motions, dual in the sense of linear programming, and I told Abdo that you love that, it's Farkas lemma as usual, okay? So the punchline is that this corresponds exactly to what we need for the proof of our periodic version of Maxwell theorem. So without the proper definition of periodic frameworks and periodic deformations, we would not have had this notion of stress, and we would not have had this theorem. Let's just be very clear about this. Okay, so this is it. So we have this theorem. So now let's look at an application. And this is the theory of expansive motions. So let me again introduce it quickly in 2D. So this is a 4-bar mechanism. In fact, it moves. And as it moves, each time this distance increases, the other one also increases. Yeah, so this is an expansive one, is where all the distances that are not fixed, they all increase simultaneously, all of them. So that's an expansive 2D mechanism. And of course, the property holds only for a certain interval in its trajectory, because at some point it stops being expansive, and at this point, one of them decreases, the other increases, right? So it's not a property of the framework, it's a property of an interval of its configuration, of one of its trajectories. Okay, so in the plane, the planar finite expansive mechanisms are fully understood. So this is my result from 16 years ago. And the 1 degree of freedom expansive mechanisms are essentially pointed pseudo-triangulations with a missing convex hull edge. So what it means, it's a planar graph, non-crossing, but every vertex is incident to an angle larger than pi. This is called pointedness. It's pointed. And when you put the maximum number of such edges, the faces of this subdivision are what is called pseudo-triangles. They can be triangles, but they are faces that have exactly 3 convex vertices. So in other words, the faces are as non-convex as possible. It's the opposite of convexity. And these objects have magic properties, but in particular, they are 1 degree of freedom mechanism and always expansive. So everything expands. Planar, non-crossing, and so on. Okay, so I said essentially because as they move, actually certain pieces stay together. Those are the rigid clusters, yeah? And they can be tiled differently. Okay, good. So now, periodic case, planar, pointed maximal, periodic pseudo-triangulation. You can build it arbitrarily, and you can have an infinite supply of such objects. And the theorem says that these are 1 degree of freedom, expansive. They have no singularities in the expansive intervals, and this property holds for any relaxation of periodicity, and they are auxetic. And if you add extra edge, they become what is called ultra-rigid. So here's how they move. Yeah, so this is a periodic mechanism in motion. And the main ingredients for proving it are the version of the Maxwell theorem, and I'm going to skip this. And I'm also going to skip the extension to periodic Bodian frameworks. It's essentially a Maxwell and Laman theorem, because I want to get in my last minute, I'm going to also skip applications to proteins. I want to get even ultra-rigidity I'm skipping, because I want to get to the auxeticity. So remember this, I showed you in the beginning. And now I think you see that this one is pointed. It's not quite pseudo-triangulation. In fact, it has 2 degrees of freedom, and they didn't know, meaning that not all the deformation trajectories are auxetic. Okay, so you have to try to understand what those are. And auxetic materials, basically there are these two examples. This one is pointed and is related to pseudo-triangulations. This one is not, definitely not pointed. So we needed a definition that is stronger than expansiveness, and this is the definition. So we have a one-parameter deformation of a periodic framework is auxetic if you have two times, so now this is the finite definition. So the linear operating taking the period lattice at time t2 to time t1 is contractive. Yes, it's an operator of norm at most 1. And this is equivalent to a one-parameter deformation of a periodic framework is an auxetic path, if and only if the curve given by the Gram matrices of a basis of periods has all velocity vectors, the tangents, in the positive semi-definite cone. So that's the connection that I wanted to get to. Okay, this tells me that I'm done. So 1 second. So 30 seconds. This is analogous to causal lines in special relativity. So the curves with all their tangents in the light cone. And in fact, the analogy is exactly the same because for 2 by 2 symmetric matrices, they form a 3-dimensional Minkowski set space, and then the auxetic trajectories for dimension 2 have associated curves of Gram matrices, which are exactly causal lines in the Minkowski space. And this leads to this topic of infinitesimal auxetics and the fact that periodic frameworks with infinitesimal auxetic capabilities have non-trivial spectrahedral cone of auxetic infinitesimal deformations. And because we are in a fixed dimension, in fact, we can decide whether it has, we have decided with one of the known algorithms that it is auxetic or not. And also we have that expansive implies auxetic, so meaning that with that previous theorem, we have an infinite set of designs. You can design your own materials in that fashion. And it turns out that sometimes these mechanisms, when they stop being expansive, they are still auxetic. And currently, we are working on the 3D things. So putting everything together, in 2D, we have an infinite supply of possibilities for auxetic periodic design, and in 3D and higher, we have uncovered infinite families, but we have not been able to characterize everything because it's much harder, as we all know. So I'm finishing with this animation, and this is a summary of the theory that I presented. I didn't have time, of course, to talk about algorithms, but I hope I made you curious about the application, so questions.
Thank you. Any questions?
Yes, Bob.
I have a comment and a complaint. Okay, first comment is that a lot of this theory, or some of the things you're talking about, are closely related to problems of packets, of disks in, I think of the things as disks in a torus. So there's one type of deformation that is interesting. One is that you allow the packing elements to move, and let's say you fix the lattice and let the packing elements move in the lattice. Then it turns out that if the packing is rigid, then it's if and only if the corresponding strut framework is infinitesimally rigid. So it's exactly the same thing you're talking about. You have a framework, you want the framework to be infinitesimally rigid, only there's a question of a stress that has to exist for a strut framework. So that's fine.
But you are working with a fixed lattice, right?
Hang on.
Okay.
So one way is to work with a fixed lattice. So in some sense, you can tell if you have a maximally locally dense packing, then you can detect whether that's true by using this rigidity theory. So that's useful.
Which rigidity theory? Which one? Which one? Which
Infinitesimally rigid frameworks. Well,
Finite?
Strut frameworks.
Finite? What
It's
kind of theory? I
It
want
is
you to give me a
in a
precise
fixed
definition.
torus. Let me finish.
Okay, okay.
Let me finish. You
Okay.
have a fixed torus,
Okay.
and you want to deform the framework of the fixed torus. So that's the first thing. Now, there's an extension. One extension is to change the shape of the torus. In other words, change the lattice, to vary the lattice. Now, it's natural to fix the volume or the area of the torus as you change. It turns out the infinitesimal theory still works. There's a number of constraints, and the number of constraints increases, but that it works out very nicely. It's essentially a theorem of Swinnerton-Dyer years ago. Okay, that's one kind of deformation. The other kind of extension is that you have a lattice, and then you take a sublattice. I think of that as a covering of the original lattice. You talked about the same sort of thing.
Yeah.
Right, so that's another kind of thing. And if you have something that's rigid, a packing that's rigid, and if it's just rigid, in a sense, and you take a sublattice, it's not rigid again. Because if you have the minimal number of contacts, when you go to the sublattice, you need more contacts generically. But never mind, you can still do that. So there are these two different notions of extending the lattice. You can take a sublattice, you can allow the torus the thing. Each of them require more constraints, and generally it allows the number of constraints such that when if you have one, the number of constraints should be enough for the other. But as it turns out, those two conditions are independent. You can have one that stays rigid when you go to finite cover, and one that stays rigid when you go to finite cover but doesn't change when you change the lattice. Sometimes it's called strictly jammed, stuff like that. So that's just my comment. Okay, that's the comment. The complaint.
Excuse me, may I reply a little bit to your comment? So what I heard from you is that all the cases that you are referring to are special cases of our theory. So our theory is a little bit more general. So I'm not saying that people have not proved those theorems. I just wanted to present this general theorem. And whether those are special cases of this, I thank you very much for bringing them to my attention, and I would very much appreciate the references so that we can properly refer to them.
Right, right. But this notion that in fact, this notion of, I think you call it, what do you call it? Ultra rigidity. I think we had another name for it. And this is also related to the
Is this a
Rumsfeld.
complaint, Bob?
Ma'am?
Is this a complaint, Bob?
No, not yet.
Oh, okay. Can you get to the complaint?
Okay. The complaint is that if you do that, if you take something that's generic, maybe it's a question and complaint, and then go to a sublattice, it's not generic anymore. That's my complaint.
Okay, and?
This is a question. So
what yes.
Yeah.
So, okay, let me tell you one thing. I never claimed that we have exhausted everything that can be said about these objects. I wanted to bring to your attention that there are a lot of problems that can be addressed in this framework or in related frameworks. And it would be wonderful if we could put all these things together where we came to this trying to answer a question, and we are not familiar with all the literature in the world. We did our best to investigate the literature. We appreciate everybody's help in enlarging our horizon and connecting these things together. So that's what I'm saying. I think that there is a wealth of problems to be addressed here, and to the best of my knowledge, we chose the word ultra-rigidity because we couldn't find.
No, I'm complaining about.
Okay,
the
wait,
rigidity. I'm
stop,
complaining about
please,
the-
please.
Whether
stop.
that existed, I'm not aware of the theory
Eliana,
being developed in this.
I think this
Yes.
you can discuss
Yes,
later.
absolutely.
Let's take another
Yes,
question
yes.
and then we'll go to
I
lunch.
have a question. So we have been showing very interesting result on the case of two-dimensional infinite periodic lattice. So what about if you have a finite periodic only in one dimension but three-dimensional object? For example, the alpha helices in a protein, which can transform in beta strand. Would it be possible to have a similar kind of theory with
I think
lifting in a 4D space?
Yeah, I think that it's a wide open thing. Yes, it's just I was suggesting a tool that might be useful or may not be useful, or maybe some other tools may be useful. So I definitely don't claim to have to see a theorem that you can take off the shelf and directly apply to your a problem. So it's an interesting thing to be.
But there's such kind of approach, because if I correctly understood, you are able to completely enumerate all the possible way to deform your lattice, or I didn't somehow, because when you are saying you have the dimension of
The dimension, it's a continuous, it's a space, it's a algebraic variety, very much like, you know, a line, a plane, a 3D piece of the space. We can measure the dimension, but unless the dimension is 1, when you have a well-defined trajectory, then if you have a 2-dimensional space of deformation, you have many trajectories, and how to choose one, so it's never a unique one once the dimension is beyond.
Okay,
yeah, so that's.
Okay, thank you. Wait, Paolo, short, please.
Yeah, sure, person. So it's a similar theory for quasi-periodic structures like these Penrose tilings.
We have not looked into that. That's too much to be done. You are welcome.
Okay, well, thank you very much.